So, today we are going to talk about zeroth law of thermodynamics. So, before we do that, we have to first make the basis clear, and we will start with thermodynamic systems and variables. So, what I mean by that thermodynamic systems and variables is that in order to understand the properties of thermodynamics, first we have to define the system and the surrounding. So, here you can see that system is in a closed region of space. Around that everything else can be called as surroundings. Right now we have drawn that using some rectangle or something. It will be clear later on what they mean. System can be of other type where one side is open and the surrounding can be a closed one. So, it entirely depends on the observer who is going to measure thermodynamic properties of a particular object to define its own system and the surrounding. So, system is defined as thermodynamic system is the part of the universe. By universe I mean physical universe, the universe in which we live in real sense, that is what is meant here, that is under consideration for calculation of the thermodynamic property. So, we can say that a glass of water is a system and everything else apart from that glass of water is the surrounding. As I said, surrounding is the rest of the universe, and boundary which separates the system from the surrounding, the surface. So, here we can say that this part is the boundary, here this part is the boundary. So, to give you a better idea of the system and surroundings is that we have taken a picture from NASA's website, the early universe picture. So, this is what universe used to look like, one of the earliest picture of the universe, and in which we have put a bottle. So, it is not up to scale, okay. The picture is not up to scale, you can see that. So, let us say the bottle is the system, everything else apart from the bottle in the whole universe is a surrounding, and system plus surrounding, as you can see, is the universe. So, this universe, when we mean universe, is actually in real sense it is the physical universe in which we live in, and you will see that it becomes very clear when we decide that as a universe and do the calculation, physical universe I mean. So, now let us discuss a little bit of type of systems which will be useful or which we need to use in order to calculate certain properties. One is called isolated system, in which no exchange of mass or energy will take place, and it is depicted in this kind of picture that the mass and the energies is conserved within this particular system. And an example of that is a thermoflax, although it is not totally an isolated system, but it is somewhat close to an isolated system possible. We have a thermostat here, a thermoflax here. So, you know that a thermoflax is meant to keep hot water hot and cold water cold to some extent. So, here we have some hot water kept inside, and outside it feels the normal temperature. However, the temperature of the water inside it is actually high. So, so it will preserve this particular hotness of water for some more time. We can say that it is a prototype of an isolated system. So, then isolated system is in which there is no transfer of energy or mass, and then there is something called closed system, which might be little bit confusing when you hear for the first time. Closed, it is closed means it is only closed for mass to transfer. So, it is not closed for energy to transfer. So, exchange of energy is allowed in this particular systems, but exchange of matter is not allowed. So, at equilibrium this particular system has a fixed number of molecules, fixed volume and fixed temperature, and in the isolated system at equilibrium we will have fixed number of molecules, volume and energy. So, an example of a closed system we can say, we can take for example this particular bottle, which will allow the exchange of energy, although you can see that the bottle is pretty closed, and what we mean by close is that no mass will be transferred outside of this. So, if we have 1 liter of water in the beginning, it will remain 1 liter after some time also. However, right now I can feel that the water is hot, but after some time it will cool down. So, there will be a transfer of energy from the bottle to the surrounding. So, this is an example of a closed system. So, it is closed, however, energy transfer is allowed. And then the third system is called open system, in which both mass and energy or matter and energy transfers are allowed. So, exchange of both mass and energy allowed, and typically at equilibrium this kind of systems will have a fixed chemical potential, volume and temperature. So, right now we are not defining these quantities chemical potential, volume, temperature, but soon it will become clear. Only thing you can actually right now take is that certain properties of the system will remain fixed in all these three different kinds of systems. So, for an open system we can easily take an example of this particular water, and I open that and I can it is hot, so I cannot drink from this. However, as you can see that there are water vapors going out from that. So, therefore, the mass content of this water is actually changing with time, and therefore, energy is also changing. When the mass can transfer between the system and the surrounding, energy also will transfer along with that. So, literally an open system is an open bottle, and that is given in this particular example here. Now, let us define variables. So, define systems, now we will define variables. Variables are of two different types. One is called macroscopic variable, another microscopic variable, another is macroscopic variable. What do we mean by that? Will become clear in a moment. So, macroscopic variables are that, so there are only very few number of variables required to define the state of the system in equilibrium. These variables are measured using available experimental techniques. So, for example, volume is a macroscopic variable, temperature will be a macroscopic variable, pressure will be a macroscopic variable. They are all macroscopic variable for measuring properties of a system at equilibrium. So, let us say if I go and ask in a shop that give me 1 liter of water at room temperature. So, what we are specifying there? We are specifying the volume, we are specifying the room temperature, which is temperature, and we do not have to specify, but it is quite understood that we are also specifying the atmospheric pressure. So, we are already specifying three different macroscopic variables. What we are not specifying is enormous number of microscopic variables that are hidden within this fixed value of macroscopic variable. What do I mean by that? So, is that microscopic variables are basically positions and momentum of all particles constituting the system. So, when I talk about a bottle of water at room temperature, if I wanted a microscopic description of the same, then I would have to specify the positions and momenta of all the atoms of that particular bottle of water, and in fact they will be all the time changing. So, let us say if I talk about 1 liter of water, then 1 liter of water at room temperature and pressure typically has 55.5 moles of water, right, and we know that 1 mole contains 6.023 10 to the power 23 number of atoms, molecules, and then in water you have 3 atoms, and then we have to specify positions x, y, z and momentum p x, p y, p z. So, therefore, 6 different variables. So, typically for n atom system we have to specify 6n number of variables. So, that means that for 1 liter of water, when I have to specify, I have to specify 10 to the power almost 26 number of variables in a microscopic sense. So, microscopic variables again mean that positions momentum, and you will see later on that given that information of position and momentum of all the particles of the given system, we will be able to calculate every thermodynamic quantity of that particular system. We will discuss more about that later on. Variables also can be of two different kinds. One is extensive variable, another is intensive variable. Extensive variables are something which scales with the size of the system. For example, number of molecules. if I take 1 liter and take another liter of bottle of water, and then when I add them together it will become 2 liters. So, that means volume is an extensive property because it scales with the size of the system. Number of molecules also 1 mole plus 1 mole will become 2 mole. Similarly, there is intensive variable which variables which do not scale with the size of the system. For example, if I take temperature of one particular bottle of water and then I measure temperature of another particular bottle of water, when I mix them together, if those temperatures were initially same, then when I mix them together the temperature will still remain same. So, let us say I take a bottle at 30 degrees centigrade, I take another bottle of water at 30 degrees centigrade, I mix them, I get double the volume, however, temperature remains the same. Or let us calculate the pressure of this particular room in one corner and another corner and then calculate for the whole room, you will still get the same pressure. So, temperature, pressure are intensive variable which will not scale with the size of the system. So, here T plus T remains T and V plus V will be 2V. Now, we discussed about the variables description in equilibrium. So, when I say that 1 liter of water, I mean that 1 liter of water at room temperature at equilibrium. So, for example, if I take this particular bottle of water and I pour some water here initially when I am pouring it, while pouring it the system is not an equilibrium. You can see there is bubbles, there will be small waves in the water and all that. After some time again things will become normal. You throw a stone at a pond, initially you will see there will be water waves going on, after some time things will become again stagnant the way it was before. So, equilibrium is something in which the observable, the one that we are looking at, let us say we are looking at height of the water, when the observable does not change appreciably, or appreciably by we mean that within the measurement of within the error of our own measurement. So, let us say we say that okay, if the water level does not change more than 1 inches, then I will think that water level remains constant. So, if the property does not change appreciably within the limit of our observation, then we say that the system is in equilibrium. For example, the water level, if you look at for a month, you might find that water level has changed because of rainfall, because of extra water from somewhere else and things like that. So, within a span of a month or years, that particular thing may not be at equilibrium, but within a time scale of let us say 1 hour, you see that it is perfectly static. For example, we look at this water in the beaker. Right now it looks perfectly all right, stable and at equilibrium. However, if I leave it for a year, there water will vaporize and there may not be any water there. So, therefore, in a time scale of a year it is not in equilibrium. So, for equilibrium we have to say that a system is in equilibrium where there is no measurable change in the system during the course of our observation. So, a glacier typically will change it in the time scales of years. When you talk about interstellar systems, so their time scale is even larger. So, always while calculating equilibrium property we have to talk about the time scale of observation and the constraints that we have associated with that. So, macroscopic variables do not change during the course of observation, but microscopic variables change all the time. So, what I mean by that is this water looks perfectly all right, looks like it is in equilibrium because there is no bubble, there is no change appreciably and all that. However, the water molecules that are there within that bottle, they are constantly changing with time. So, they are not static. Although the overall system is in equilibrium, each molecules is actually dynamically changing with time. So, so to give an example of a microscopic variable, I can show you this particular picture where the water configurations are given, and this particular bottle is an example of a macroscopic variable where you do not have to look at the microscopic object. So, microscopic means small, macroscopic means big. So, when you talk about macroscopic variables, we are talking about variables associated with large quantity. When you talk about microscopic variable, we are talking about variables associated with atoms and molecules. So, here is an example of looking at the molecular level, here we are looking at the level of macroscopic quantity.